Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is the second one in a series on derivatives of polynomials. The first one is a must watch because it showcases the theorems and the proofs required so that we can actually do the mathematics we're going to be doing in this video. Computing derivatives of polynomials is pretty straightforward though. Once you have those theorems with you, you are guaranteed to ace your way through this material. This is the easy part of calculus, I like to say. So I try to still throw at you curveballs just to make sure you're thinking rather than just copying and rote doing things like that. So find the derivative of this function. Now let me just tell you, we have a theorem that we were introduced to last time. In fact, I'll just hop back to it. That if you have a sum or a difference of functions within a derivative, you could break that apart into the derivatives of their sums or differences. That is, you could break up derivatives across addition or subtraction. However, when we went through and proved that, at the very bottom, I put a big old warning. And I said, this does not say that you can take the derivative of a product and break that apart. That is not true. Derivatives of products do not break apart nicely. So if you're facing a product, try to do anything else other than just taking the straight derivative as written. So here we are facing a product. What do we do? Well, that's pretty easy. We do algebra before we do calculus. This is x to the fifth. So now I'm ready to go. And f prime of x, according to our previous theorem, we drop the exponent down and we reduce the new exponent by 1. That's it. Done. By the way, again, notice that this is not the derivative of x squared, which is 2x to the first, times the derivative of x cubed, which is 3x to the second. It is totally not that. Completely different numbers. So that's just to illustrate why taking the derivatives of each factor within that product is not the same as the actual true derivative. Again, I'm still trying to get you to think at a higher level, right? Get prepared for some terrible problems or whatnot. And this function does look fairly terrible. It doesn't look fun at all. The very first thing you should probably do is note, I did not introduce you to a theorem that said, oh, if g is just the quotient of two functions, f and k, then that implies that g prime is equal to f prime over k prime. That's not true. Totally not true. So the only type of derivatives that you can split is if your function, I'll just call it h, is equal to f plus g or minus. Then the derivative of your function is f prime plus or minus g prime. That is true. But quotients and products you cannot break apart with derivatives. So what do you do? The answer is pretty simple. Perform arithmetic before algebra, algebra before trig, trig before pre-calculus, pre-calculus before calculus. So we're going to simplify this using good old algebra. And I don't mean factoring. I just mean actually clean this thing up. Like use your algebra skills. There's quite a bit that you can do here. For example, this, and in my pre-calculus class, my pre-cal students, I keep harping on them right now, saying you're going to have to be able to work with radicals and switch them to rational exponents because that's what you would prefer in calculus is rational exponents. So that's what we're going to do here. We have this 18x to the third, and it's being multiplied by the sixth root of x to the fifth, which is the same thing as x to the 5/6, as we know from our prerequisite material. So you are fine with that. Minus 10 times x squared, again, times x to the 5/6. Let's see, minus 3 times 10x being squared, well, that's 3 times 100x squared, or minus 300x squared times x to the negative 1/6. And finally, plus 45x to the 4/3. It's already prepped for us. Downstairs, we'll go ahead and say that's 5, and then we're going to square the 3, so times 9, and apply that square to the x to the 2/3. Remember, powers raised to powers will multiply. So that's 2/3 times 2, or 4/3, x to the 4/3. We're almost ready. Still a little extra work left here. So let me zoom in. This is equal to 18. Let's see, x to the 3rd. That's the same. 3 is the same thing as 18/6. And so 18 plus 5/6 is going to be 23. Oops, x to the 23/6 minus 10. Let's see, that's x to the 12/6 plus 5/6, x to the 17/6 minus 300, x to the 11/6, if you do that mathematics. And the last one is already pre-cleaned up for us, so we don't have to worry about that. And this is all over 45 x to the 4/3. And now I can break that into 4 separate fractions, right? Just really quickly, this is 18 x to the 23/6 divided by 45 over x to the 4/3 minus 10 x to the 17/6. I'm going to pause the video and just finish this out. And there we have it. Really nicely done. Now, just need to reduce that. And we use laws of exponents for that. And rather than me painstakingly telling you what I'm doing, this is from your Algebra 1 course, so I don't even need to explain what's happening here. So using our Algebra 1 and Algebra 2 skills, we reduce it down and our arithmetic skills, we reduce it down very quickly to this. Now, I haven't even started the derivative yet, but we've reduced g down to that. Now I can do the derivative. G prime of x is equal to, remember, we have a theorem that says that you can break apart a function into its component terms. So we can look at the derivative of 2/5 x to the 5/2. I'll circle up. Actually, I'll highlight. We could that's not a highlighter. We can look at the derivative of this, and then move on to look at the derivative of this, and then move on to look at the derivative of this guy right here. And the last one, the derivative of 1, we know is 0. Here we go. 2/5 times 5/2 x to the 1 less than 5/2 minus 2/9 times, bring down the power, 3/2, x to the 1 less than 3/2 minus 20/3, bring down the power, times x to the 1 less than 1/2 power. And all you need to do here is clean things up. So the derivative of g is x to the 3/2 minus 1/3, whoops, not equals, but minus 1/3. Let me just double check. Yep, x to the 1/2, and minus 10/3 x to the negative 1/2. That is g prime of x. That's the derivative function. The interesting thing to note is when asked to find the derivative, that means that for that ugly function up there at the top, we now know the slope of that curve at any given moment. I should say the slope of the tangent lines to that curve at any given moment. To find the slope of any tangent line to the curve, g of x, I could just look at g prime and plug in the x value. I don't want to do it, but I could do it. Now, as you could tell, the derivatives may look really ugly, but they actually are not. They're all the same thing over and over again. Bring down the power, reduce 1 from the power. Bring down the power, reduce 1 from the power. And so you can get really interesting examples like this guy right here. H of x is equal to the pith root of x. First of all, just use your good old algebra to rewrite that as 1 over pith power of x. And this is a reason why I tell my algebra, college algebra, and pre-calculus students that radical notation is not going to help you in calculus. It's really rational exponent notation that you want to stick with. And this is a great example. The derivative of h, you're going to bring down that exponent, and you have x raised to that exponent minus 1. And that's about as good as it gets. Now, something I need to note here, not just with this example, but with all the previous examples, is that when you're dealing with a function and you're asked to find its derivative, you're taking, especially with the theorem, let me hop back actually 2 spaces here. This theorem right here that we proved last video. That theorem is incredibly powerful. It's also incredibly abused because people want to use that theorem when they should not use that theorem. Remember, I will say this as often as I can. Mathematics is a list of rules. If you are not good at following rules, you will not be good at math. If you're not good at reading, you're not going to be good at math. If you're not good at following instructions, you're not going to be good at math. A lot of people think that they're bad at math when in reality, they're just bad at following instructions. That's really it. So the instruction here is, this rule is true. It is. It's totally true. If you're taking the derivative of something like x and it's being raised to a power that is a number. This does not say, however, if I take the derivative of some number raised to the x power, it's not saying that that is, oh, bring down the x and that's the number to the x minus first power. That is not what it's saying. It's saying if your variable is in the base, that's critical to note. The variable is in the base, and that is the only way that this theorem works, is if the variable is in the base, not in the exponent. We will run into examples where the variable is in the exponent, but not in this video. So all of that being said, find the derivative of this final function. K of x is equal to pi to the eth power. Something you should note about that. Is there an x? There's not even an x in that function. This is just some number. It is a constant. So be very vigilant, hyper aware. Don't just run through mathematics without thinking. Look at that and go, oh, that's just some number. It's just a constant. And the derivative of a constant is always 0. So be very, very careful when you go through and do mathematics, because you'll end up just thinking, oh, I'll always drop down the power and subtract 1 from the power. Nope, that's the rule if your base is x, but your base here is not x. It's just a finite number, a constant.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.